All right, yesterday we started working with the law of sines and areas of triangles. Once again, using law of sines is a lot easier to work with using laws of sines. And problem number 5 in finding the area of the triangles. You would have to use your law of cosines to find an angle. Okay, now it does not matter which angle you find, but you can use your law of cosines to find one of those angles. So in problem number 5, you have triangle map. Okay, you draw your triangle map. Once again, as we talked about yesterday, to find the area of a triangle, we are given here the value of M is 6, the value of A is 9, and the value of P is 13. And we need to calculate the area of this triangle. To calculate the area of the triangle, we need to take the product of any two sides, which means we're going to multiply the lengths of any two sides together and multiply it by the sine of the angle included. Well, what we are given there is we are given all three sides. And we don't know any of the angles. So what we must do is we must find one of those angles. Well, to find the measure of one of these angles, we have to go back to what we did yesterday. What we did yesterday with the law of cosines was when we have all three sides of a triangle, we can use our law of cosines to find the measure of any angle. Now, once again, at this point, you can utilize law of cosines to find that angle. You can find any of the angles, and it does not matter which one you find. Typically, and this is just me, this is my old man brain, okay, and it's stuck in a routine of how things are going. What I always do is I use my law of cosines to find the measure of the biggest angle if I have all three sides. The reason why is eventually what we talked about today, we can use our law of sines to be able to find measures of the angles. If you have an obtuse angle with one of your angles, okay, if you have an obtuse angle, it's going to occur across from the biggest side, because in a triangle you can only have one obtuse angle. Okay, you can only have one obtuse angle. So with only one obtuse angle, how do I find the obtuse angle? Well, that's going to have to be across from the biggest side. So I look at that with respect to calculating that. So that's just how I deal with that, and that's how my brain works, is I'm going to find angle P. Reason why is across from the biggest side. If it's going to be an obtuse angle here, then it's going to occur at angle P. So I always find angle P. Well, if I'm looking at my law of cosines, I have the cosine of angle P at the end. Now, if you've already done this problem and you've picked another angle, or if you want to choose another angle, that's fine. I'm just telling you how I go about it, how my old brain works. Okay? But if you found another angle and did this problem using another angle, you should come down to the same solution. Okay, so write yourself a law of cosines. If you haven't done it, write yourself a law of cosines equation with the angle cosine of angle P at the very end. And then start substituting in the numbers. So we have P squared equals M squared plus A squared, or A squared plus M squared, does not matter once again. Minus 2 MA or AM does not matter, cosine of angle P. Once again, hopefully you have that written down already. And if you chose another angle, that's fine. If you said cosine of angle A, then you have a squared at the beginning. Then you have m squared plus b squared. Does not matter which angle. Okay, substitute your numbers in. Now we have to solve for the angle, so we have to subtract our square terms over. Subtract your square terms over, and then get one coefficient using -2 times 6 times 9. Once again, get one coefficient. Do not lose your negative sign with this. Divide both sides by your coefficient. And to find the measure of angle P, we could take the inverse cosine of our fraction there. Once again, you should be working ahead. You should not be sitting there just going, doing Sandlot studying here, Sandlot learning, and saying, oh, yeah, that's what I do, and write it down. You should be working forward in front of me. Because you don't learn through the process by just copying down what I have and saying, oh, yeah, that's how you do it. Yeah. Come on, yeah. That's a great movie. Benny the Jet. Oh, I don't know. I could be wrong too. At 108. There we go. That's why you don't sit there and just copy my stuff down, because old man brain sometimes makes mistakes. Can't be perfect all the time. So we take our inverse cosine of both sides, find the measure of angle P. Ethan, what do you get for our measure of angle P? You go with that? So what that gives us is this gives this angle right here. Now, once again, this is KYC. Know your calculator. Okay, you just did this and calculate that angle. And you have a nice long decimal sitting down there. To calculate the area, I found this angle. I had to take 1/2 times the product of these two sides times the sine of the angle included. So you can just pull your answer down. On the next line, you can take 0.5 times 6 times 9 times the sine of second and your negative sign. That pulls your answer down from the previous line. Once again, KYC, know your calculator. Jacob, what do you get for area? 23.66. And that's in square units. Okay, we good with that? And if you did the homework problem and you found A or M, you should get something very close to that. Once again, pennies off here or there just because of rounding, what we do with respect to rounding. Second section dealt with the law of sines. Working through the law of sines. Once again, just write out your law of sines ratios. You're going to be given 3 of the 4 values. Once you know 3 of the 4 values, you can find the 4th value there. Questions about law of sines? Once again, the hope is that you have quite a bit of recall, or not quite a bit, some recall from geometry. Where this won't ooh and ah you. It's not like trig identities where you never dealt with a half angle, double angle in geometry. Today we're going to use the law of sines and cosines to solve a problem. But there's another issue that we have with solving the problem. So everything we do today deals with still law of sines and cosines. We have a triangle. We have a triangle. We want to solve for little a. Okay, we want to calculate little a. We know 2 sides. We know 2 sides of the triangle. We know 7 and 8. And we know an angle that's not included in those 2 sides. But we want to solve for angle A here. Well, how do we go about doing this? Well, what we know is we know law of sines and law of cosines, where, you know, law of sines is the easiest one to work with. We have sine of angle A over little a equals sine of angle B over little b equals sine of angle C over little c. I want to calculate A, but I don't know big A. Well, if I want to calculate A using law of cosines, I have A squared is equal to B squared plus C squared minus 2BC cosine of angle A. But to solve for angle A in this method, I need to know, or solve for little a, I need to know angle A. I don't know angle A. So dealing with this is going to take a few steps to be able to solve this problem. But what I do know is I know angle B, I know little b, and I know little c. So in my proportions or my ratios, in my last 2, it doesn't solve me anything for A, but it allows me to take the sine of B, angle B over little b, and set that equal to sine of angle C over little c. It allows me to at least solve for angle C, because I know 3 of the 4 of the ratios, or in the proportions. So let's set up our law of sines and solve for angle C. Sine of angle B over little b equals sine of angle C over little c. So we have sine of 50 over little b, which is 8. Sine of angle C, don't know angle C, but I know little c is a value of, let's see, that should be 7. I know angle, or a little c is a value of 8. So I could cross multiply and divide, and that's going to give me the sine of angle C. I'm going to get sine of angle C is equal to some decimal. To solve for angle C, what would we have to do to both sides to solve for angle C, Paul? Sine of angle C is equal to some value. I want to solve for angle C. How do I get rid of that sign? How do we get rid of sine in our equations? Inverse sine. So I can take the inverse sine of my decimal I created. So I take my inverse sine of my answer that I come up with. And that will give me the measure of angle C. So I take my set inverse sine of my answer. Once again, KYC, know your calculator. Jade, what do you get for measure of angle C? 61 point what? Okay, 61.1. So that's the measure of angle C. 61.1. Whoops. Which now, using properties of a triangle, can we solve for angle A? I know angle B is 50. I know angle C is 61.1. What's the measure of angle A have to be? Lucas, what's the measure of angle A have to be? 68.9. How'd you get that? Okay. I know the measure of these these angles have to add up to 180 degrees. So I can take 61.1 plus 50, then subtract that from 180. And what that gives me is angle A. So I know now angle A. So going back to these two ratios, I can solve for little a. I have the sine of angle A over little a is equal to sine of angle B over little b. So we have the sine of 68.9 divided by little a, which is, we don't know, sine of angle B over little b, which is a value of 7. So we can now solve by using law of sines the measure of little a by cross multiplying, dividing. Once again, we are just applying our law of sines and law of cosines. Maddie, what do you get for little a? 8.52. Good for that? Yes, no, maybe so. We good? And if we take a look at our triangle, okay, 8.52 is my biggest side. It's across from my biggest angle. 50 degrees here is my smallest side. That's across from my smallest angle is across from my smallest side. So I'm anatomically correct in regards from biggest side across from the biggest angle, smallest side across from the smallest angle. Okay, and we did everything correct there. But the problem we run into with this is if we go back to our original triangle. Our original triangle was this. This was 8, this was 7, this measures angle 50 degrees. Angle C was, or angle B was 50 degrees. There is a second option for these conditions of this triangle. If we would take this side and put it on a hinge and swing it from here over to here and move the 7 over here. This is all this is an isosceles triangle. Two sides that are congruent. If this was 7, this is 7 here. I can do this triangle here. And I have the exact same conditions. This length is still 8. I didn't do anything with that length of that side. This measure of this angle, angle B, is still 50 degrees. This measure here is the same as this measure here. It's just an isosceles triangle. What I have is I have a second scenario with respect to my triangle. That is a true scenario. It's a true possibility. Well, if I take a look at my measures here, these measures look appropriate with respect to the triangle. But if I take a look, this angle here now looks obtuse. It now looks obtuse. I calculate that angle to be 61.1, which is across from, this is the middle angle, across from the middle side. The question is, how do I come up with a second angle there? How do we come up with a second angle? We did everything mathematically correct, but now I have a different scenario. How do I solve for a second solution? Well, if we take a look at the process that we did, we had the sine of 50 over 7 equals the sine of angle C over 8. We came down to the sine of angle C is equal to some decimal. And as Paul said, what we had to do in this case is take the inverse sine and take the inverse sine of both sides. Well, when we take the inverse sine of both sides, what we learned a month ago is when we take the inverse sine, we clickety-clacked it through our calculator, and we got our principal value, the calculator value. But what we learned a month ago when we were dealing with principal angles, when we did the inverse sine, do we have to worry about a second solution? When we take the inverse sine to solve a problem, we get the calculator value, which is the principal value. And also it's what, Jacob? Supplement. So we came down to 61.1 degrees for the measure of angle C. But what we also have to worry about here is the supplement. Well, what is the supplement to 61.1 degrees? If the measure of the angle is 61.1, what is its supplement? Q? 118.9. 118.9, which looks like this obtuse angle. If this measure of angle C is 118.9, the measure of angle B is 50 degrees. What's that leave for the measure of angle A? We have 50 degrees, 118.9. What's that leave for the measure of angle A? Ella? 11.1. 11.1. Now I can find little a by, once again, sine of angle A over little a equals sine of angle B over little b. We have the sine of 11.1 over little a is equal to sine of 50 over little b. We can cross multiply and divide, and we can solve for little a again. Once again, all we're doing is we're using our law of sines. You're solving proportions here. These are things that you learned back in 5th and 6th grade mathematics that you should be able to do. Cross multiply and divide. It's amazing how things that we learned in the past just keeps on coming back to haunt us a little bit. Mr. Gregory's so mean, man. He trying to make us remember what we did in 5th and 6th grade. Solving proportions. That's outlandish. Ludicrous. He's gone to plaid. Ash, what did he come up with? What do you get for little a? What? 1.76. Good with that? So we have 1.76 down here. If we take a look anatomically, 1.76 is my smallest side. Here's my smallest angle. 118.9 is my biggest angle. This is my biggest side. Middle angle, middle side. So I have an anatomically correct triangle. So basically we have two solutions here. Two possible solutions. With the exact same conditions. Initial conditions. So this goes back to your geometry days. Okay, your geometry days, when you're sitting there proving triangles congruent. And you learned a bunch of postulates that allowed you to prove triangles congruent. You had the side postulate. Okay, side postulate. If three sides of one triangle are congruent to three sides of a second triangle, then the two triangles will be congruent. Then you learn the second one. Which was the side postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles will be congruent by the side postulate. Then you learn the side angle postulate. If two angles in the included side of one triangle are congruent to two angles in the included side of the second triangle, then the two triangles were congruent. Then you learn the angle side postulate. If two angles in the non-included side of one triangle are congruent to two angles in the non-included side of a second triangle, then the two triangles were congruent. And these are all postulates that you learn in geometry and proving triangles congruent. But what we have here is we have two sides of one triangle congruent to two sides of a second triangle and a non-included angle. So somebody, as you were going through all these things with Dr. Clark or Miss Fennell down there, sat there and went, well, we have side, 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 angle, side, angle, side, angle, 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 side. Where's our angle, side, side postulate at? Where's the angle, side, side postulate, Dr. Clark? Why don't we have an angle, side, side postulate? Why don't we have that? I might be old, but you're not baiting me into it. And the reason why is what we just have right here. We have this scenario right here. Two sides of a non-included angle congruent to two sides of a non-included angle of a second triangle. These two triangles, you cannot put one on top of the other and say they're congruent. Now, what you can have is a corollary. This would be true. Corollary is an offshoot. This would be true if the angle was obtuse. If the angle was obtuse, then the two triangles would be congruent. But we don't have that. Okay, it's a corollary that they should add to geometry and Euclid and all that stuff and call it the Gregory corollary and be done with it. So I could be like a guy. You talk about history of mathematics. There's a mathematician, his name's L'Hopital. L'Hopital is a French guy. L'Hopital. You'll learn about it if you go into calculus next year, get into the calculus world, you'll learn about L'Hopital. We'll talk about L'Hopital a little bit. The sordid tales of the math world back then. L'Hopital was one of those people that he was a wannabe. He was a wannabe. He wanted to be this great mathematician and have he wanted to be like Pythagoras over there and have something named after him. So what he did, he paid a guy named Johann Bernoulli some hush money. 500 francs a month for naming rights, basically, of what is now called Bernoulli's rule. I'm sorry, L'Hopital's rule. Paid hush money to Bernoulli for naming rights, basically, to have a rule in mathematics that's called L'Hopital's rule. And he paid hush money to do that. The sordid stories of mathematicians. Well, I don't want hush money. I just want it named after me. So. On page 239. On page 239. You're asked to solve, ask you to solve the triangles. Yeah, the multiples of 3 to 27 multiples of 3. They're asking you to solve the triangles. What do they mean by solving the triangles? In each case, you're given triangle A, B, C. You're given that. They're going to give you 3 tidbits of information for each of those triangles. They want you to solve for the rest of the triangle, which means solve for the rest of the angles and sides of the triangle. On the odd ones, calculate the area, just the odd ones. The answer's in the back of the book. Now, all your angles are in degrees and minutes. Now, remember what you have to do with minutes. And problem number 3. Problem number 3, you have an angle C is 23 degrees 50 minutes. Okay, to convert your minutes into decimals, you take your minutes and divide by 60 minutes because there's 60 minutes in a degree. So if you want to, you could just do the calculations. You come down to 0.83 repeating. You could just say that's 23.833 degrees. When using your law of sines to find the measure of an angle, always find the biggest side and crossing the biggest angle, because that's going to be your one obtuse angle, and the law of cosines will give you that. How many obtuse angles can you have in a triangle? 1. So if 1 is already there, you can use your law of sines. You don't have to worry about a second one. Tomorrow we'll have a worksheet starts combining everything together. Monday we'll have a worksheet and in-class assignment. Tuesday and Wednesday will be quiz and evaluations over inverse trig and law of sines and cosines. Questions you have? You get about 2 minutes here. QED. I is done.
So I finished Trig Ambiguous because I don't have